Here's a silly question for you. Can probabilities be negative? The idea sounds absurd, right? If someone told you that there is a less than 0% chance of rain today, well, you would be right to tell them that's impossible. That would be the same thing as saying that there is a greater than 100% chance of having no rain. You might be tempted to think that negative probabilities have no place in probability theory in general, and should always lead to these kinds of absurdities. But as it turns out, that's not entirely true. As Richard Feynman argued in a 1987 paper, the idea of negative probability may be no more mysterious than something like negative money, which is a concept that we use fairly often in financial calculations. What this video aims to show is that asking under what circumstances negative probabilities are possible surprisingly leads us to phenomena that pop up all the time in quantum mechanics. To demonstrate this, we'll start by building up an example where we can toy with the idea of negative probabilities in the simplest possible context. We will then learn from this example what conditions are necessary for negative probabilities to lead to reasonable results. That is part 1. In part 2, we will turn to the famous double slit experiment of quantum mechanics, and find some striking similarities between this experiment and our toy example. Discussing these similarities will bring us face to face with core ideas in the foundations of quantum theory. Are you ready? Alright, good. To begin, let's consider a source of particles and call it S. S shoots out particles, one by one, in a spread of directions that is sampled at random. Let's have the particles be collected by two boxes, which we will call 1 and 2. We can describe the system by specifying the probability that a particle will go from S to each box. Here's an example. In this case, the probability that a particle goes from S to 1 is equal to 0.7, and the probability that a particle goes from S to 2 is equal to 0.3. For clarity, let's call these transition probabilities. Although if you've taken a probability course before, you might be more familiar with the term conditional probabilities with this vertical bar notation. This is the same thing, but I'm choosing to use a clearer notation for this scenario. Now, instead of physically drawing the source in the boxes, let's abstract the situation using points and lines. When you see a line connecting two points, the number next to it represents the probability of transitioning from the point below to the point above. To use standard math jargon, I'll refer to this as a probability graph, and refer to the lines and points as edges and nodes, respectively. In order for these to make sense as probabilities, we should set a rule that the sum of the numbers emerging from any node should equal 1, so that no particles are created or destroyed in this process. Keep note of that, it will be important for later. Now that we have a language in place, let's turn to a slightly more complicated scenario. We have our source S, and now we have 3 boxes. But now let's consider 2 other objects, A and B, which capture particles from S and send them towards the boxes. Just like before, we can describe this system in terms of transition probabilities for particles moving between all the parts, and we can visualize these transition probabilities with a graph. To be concrete, let's just throw some example numbers in there. And to keep things as simple as possible, we assume there's 0 probability of transitioning along these yellow paths here, so we don't have to draw those edges on our graph. This graph contains all the information we need to describe our system, in terms of transition probabilities that always involve either A or B. But let's say now that we just want to know the probability that a particle starting from S will end up in a particular box, and we don't care about the steps it took in between. We can imagine putting a curtain over the parts involving A and B. We wish to calculate these transition probabilities, which only involve S and a given box. These probabilities ask the question, what is the probability of ending up in a box regardless of going through A or B? Our graph gives us a nice way to visualize this question. We basically want to take this graph, which contains nodes for A and B, and turn it into a simpler graph, where we only have edges that connect S to one of our boxes. And we want to know what transition probabilities to assign to those 3 edges. Those who have taken a probability course likely know how to solve this problem, but I will still demonstrate the steps with an example because it will help build intuition for what follows. Let's focus on 2 as an example. How do we calculate the overall probability of going from S to 2? Well, we should consider all possible paths that start at S and end at 2. Here we have 2 paths, which I've highlighted in green and purple. A simple yet easy strategy for doing probability calculations is to simply say in words what needs to happen for an event to occur. In this case, we might say, a particle gets from S to 2 by path 1 or path 2. In path 1, the particle has to go from S to A and go from A to 2. In path 2, the particle has to go from S to B and go from B to 2. Now it's just a matter of converting the words into math. In these kinds of graph problems, this amounts to replacing AND with multiplication and OR with addition. So we make our replacements, substitute the probabilities of going through each chunk of the paths, and just like that, we can calculate the probability of going from S to 2 regardless of passing through A or B. Without going too much into the rigor, I'll just say that the general rule looks like this. Those who are curious may try to show that these rules work in general, no matter how complicated the paths in our graph get. Applying the same strategy to boxes 1 and 3 as well, we get the following numbers for our simplified probability graph. As a sanity check, all 3 numbers are positive and they add up to 1, so they are sensible probabilities. Now the interesting question at this point is, what kinds of numbers are we allowed to put on the first graph and still obtain sensible probabilities in the second graph? You may be surprised that this does not rule out negative probabilities on our first graph. As an example, let's try putting a negative number on the edge connecting B and 2. To conserve probability coming from B, this means we need to put a number greater than 1 on the edge connecting B and 3. So let's see what we get now on our second graph using the same steps as before. Would you look at that? We still get 3 positive numbers that add up to 1. If we revisit our calculation of P of S to 2, we see that although a negative number enters that sum, it doesn't make the total probability go negative. Roughly speaking, this change we made just shifted probability from box 2 to box 3. So it turns out that if we are only concerned with probabilities of transition between S and one of our boxes, then a negative probability for an intermediate transition can lead to sensible results. But why did it turn out this way? Clearly I must have chosen specific numbers that make everything work out, right? To some extent that's true. You can't put any numbers into this graph. Sometimes negative numbers will lead you to trouble. So what's the secret behind choosing numbers that work out? The answer gives us a surprisingly deep insight. Let me point out 2 interesting features of this problem. The first is something I'll call interference. Let's run 2 tests, one where we block off the path to B and one where we don't. If we calculate again the probability of going from S to 2, we find 0.8 in the first case and 0.44 in the second case. Now stop to think about how weird this is. We opened an extra pathway for particles to get to box 2, and somehow the particles end up there less often. This is the defining feature of something we'll call probability interference, in which opening up an extra pathway decreases the overall transition probability. The second feature to point out is something I'll call which-way information. Notice that even though the probability of going from B to 2 is negative, we never directly observe this intermediate transition. In other words, we never know whether a given particle in 2 came from B. Think back to our curtain. We do not have access to the parts of our setup that contain A and B. But it's not like the particles never go through B, right? After all, each particle starting at S has a 30% chance of ending up in B. If we increase this probability, that would mean we are becoming more certain that a particle goes through B as opposed to A. Let's see what happens when we increase this probability to, say, 0.7. Running through our calculation, we see that the overall probability of going from S to 2 becomes negative, which we cannot accept as a probability for an event that we are directly observing. So it seems that the probability of going from B to 2 can be negative if we are sufficiently uncertain that particles in 2 came from B as opposed to A. The takeaway here is that negative probabilities work when we lack which-way information. By this I mean information about which way the particles went, through A or through B. This is strange terminology, but you'll see later why I'm choosing to call it this. So okay, fine. I guess technically negative probabilities can work out mathematically. But surely this is just a mathematical curiosity, right? You couldn't have a physical system that behaves this way, right? Oh, if only that were true. Enter the double slit experiment of quantum mechanics. Imagine we have a source that shoots out particles one by one, just like we had before. But imagine these particles are very tiny, comparable in size to the particles that make up atoms. These particles encounter a barrier with 2 slits that blocks their path to a detector screen on the back wall. The particles that get through are collected as spots on the wall, and we could talk about the probability density of a particle landing at a certain point on the wall. Let's start with just one slit, by blocking the slit on the right. When we run this experiment, we find, unsurprisingly, that the particles form a clumped pattern directly behind the open slit. Above the back wall, I've plotted a curve showing the probability density of a particle landing at each point along the wall, which in this case is just a bell curve centered right behind the open slit. The same is true if we instead block the slit on the left. Now what happens if we keep both slits open? If you haven't seen this before, I encourage you to pause the video now and come up with a prediction, because the result will blow your mind. You might expect that we will get the sum of the two patterns we obtained before, that is, two clumps of spots directly behind the open slits. But here's the pattern we actually get. What the heck is this? What's with all the peaks, and why does the probability seem to drop close to zero at some points? If we superimposed what we expected the pattern to look like, we find that they're almost nothing alike. This pattern is often called an interference pattern, and it is exactly the pattern you would get if you sent a wave through the slits and measured the height of the wave when it hit the back wall. So the conclusion at this point is usually that a particle, on a small enough scale, acts like a wave that goes through both slits, interferes with itself, and creates that pattern on the back wall. Oh, but don't worry, it gets weirder. Suppose we watch the slits to see which slit each particle actually goes through. After all, it's nonsense to say that a particle goes through both slits, right? A simple way of watching the slits is to place detectors near each slit, which will light up when a particle goes through that particular slit. I will call these which-way detectors. Let's run the experiment with the which-way detectors and see what happens. Do you see that? We don't get interference anymore. The very act of measuring which slit each particle goes through has destroyed the wave-like nature of the particles. This is one of the central mysteries of quantum mechanics. It is often said, jokingly, that particles only act like waves when we're not watching them. The interference only appears when we don't have which-way detectors. If you take an introductory course in quantum mechanics, this phenomenon is usually explained in terms of something called wave-particle duality, in which a particle propagates as a sort of wave of probability until you measure its position, at which point the wave collapses to being localized at a point. As long as you accept this strange notion, you can make sense of the results of this experiment by realizing that the wall in our detectors measure the position of the particle. So if our detectors are not there, then the wave doesn't collapse until it reaches the wall, whereas if our detectors are there, the wave collapses at the slits as well as at the wall. That's the standard description, but honestly, we don't need to describe this in terms of waves at all. Another way of saying what's weird about the double slit pattern is that opening the second slit decreased the probability of reaching certain regions. And what our negative probability analysis taught us is that this doesn't need to come from waves. It can come from well-defined paths whose probability contributions cancel out in some way whenever we lack which-way information about those paths. This in fact opens the door to an alternative formulation of quantum mechanics due to Feynman called the path integral formulation of quantum mechanics, but I will have to save that topic for another video. So what's the point here? Using pure logic, we determined under what conditions negative probabilities may be possible, and we found that those conditions reflect deep features in our most fundamental theory of physics. What we've essentially done is taken a peek at an active field of research called quantum foundations, a field at the intersection of math and physics that seeks to answer the question of why the strange laws of quantum mechanics are the way they are. So does all of quantum mechanics just boil down to probability with minus signs? Certainly not. There's definitely more to the story. But what we have done here does give us a taste of what quantum mechanics is truly about, and it's not about particles and waves. It's about information, and about how probabilities behave when information is fundamentally inaccessible to observers. Not bad for a silly little question, I would say.